Solar energy installations have increased by over 20% annually worldwide, yet most consumers face confusion at a critical decision point: which panel type to choose. The solar market offers two dominant technologies, monocrystalline and polycrystalline panels, each with distinct characteristics that impact performance, cost, and suitability. This analysis examines the fundamental differences between these technologies, comparing manufacturing processes, efficiency ratings, spatial requirements, and total cost of ownership. The data reveals how these differences translate into real-world performance for residential and commercial installations. Monocrystalline panels derive from a single, continuous silicon crystal structure. Manufacturers employ the Czochralski process, where a seed crystal is drawn from molten silicon to create a cylindrical ingot. This ingot is sliced into wafers, producing cells with uniform atomic structure. The single crystal architecture creates an unobstructed pathway for electron movement, maximizing conductivity. Industry standards designate these panels by their uniform black appearance and occasional rounded cell corners, a result of slicing circular ingots into square cells. The manufacturing complexity requires higher energy input and produces more silicon waste from the cylindrical to square conversion. Polycrystalline panels consist of multiple silicon fragments melted together and poured into square molds. This casting method eliminates the need for precision crystal growth, reducing both manufacturing time and energy consumption by approximately 30% compared to monocrystalline production. The resulting wafers contain numerous individual crystals with varying atomic orientations. These crystal boundaries create resistance points that impede electron flow. The panels exhibit a distinctive blue or speckled surface pattern, reflecting light differently across crystal boundaries. The square mold process eliminates material waste, making polycrystalline production more resource efficient. Monocrystalline panels achieve conversion efficiencies between 15% and 23%, with leading manufacturers reaching 24% in laboratory conditions. The uniform crystal lattice enables electrons to traverse the cell with minimal resistance. Current commercial monocrystalline modules average 20% efficiency in standard test conditions. Polycrystalline panels convert sunlight at 13% to 18% efficiency. Crystal grain boundaries scatter electrons, reducing overall current generation. Modern polycrystalline products cluster around 16% efficiency. This 4 percentage point gap translates directly to power output differences under identical conditions. The selection between monocrystalline and polycrystalline technologies depends on three primary factors: available installation area, budget parameters, and performance requirements. Monocrystalline panels deliver maximum power density and superior high-temperature performance, justifying the cost premium for space-limited or efficiency-critical applications. Polycrystalline panels offer economical entry to solar energy for installations with adequate space and moderate climate conditions. The technology gap has narrowed as manufacturing improvements enhance polycrystalline efficiency, though monocrystalline maintains its performance advantage. As solar technology advances, both panel types continue evolving. Understanding these fundamental differences enables informed decisions aligned with specific installation requirements and long-term energy goals.